In this video, we're going to go over the introductory assignment for solubility. This is on page 74 in your science booklet for advanced science, grade 9. This is the more mathematical topic in the course. Things get a little bit more difficult mathematically. However, this first assignment starts off with hopefully a little bit of an easy start. You need to have this solubility curves graph available. It's on page 115 in your book, and we also had separate individual sheets handed out so you don't have to flip back and forth. The solubility chart shows us how solubility, measured in grams per 100 milliliters of water, changes with different temperatures for a variety of solutes. The solutes are KNO3, potassium nitrate, NaNO3, sodium nitrate, KCl, potassium chloride, NaCl, sodium chloride, NaHCO3, sodium hydrogen carbonate or sodium bicarbonate, and then NH3, which is ammonia. Everything at the top here are salts. Ammonia is not a salt, it's a gas. So we can see here that for most substances, their solubilities increase with temperature. Ammonia, the gas, is a notable exception. It decreases in solubility dramatically with temperature. So we're going to need to use this graph to answer the questions on this sheet. The first problem is just a question to get you to read the graph, to read it accurately. So we want to know what is the solubility of each substance at the given temperature. Pause the video if you're doing this as a review and see if you can do these yourself. So the first one, sodium chloride at 70 degrees Celsius. So I'm going to grab my graph. I'm going to find 70 degrees Celsius, which is here. I'm going to look at sodium chloride, NaCl, that's this line here, which doesn't really change that much, does it, with temperature. And at 70 degrees, I'll go up to that graph. There we are. And now looking at the y-axis over here, on the side, on the left, we can see that the solubility is between 35 and 40. I think it's slightly closer to 40 than to 35, so I'm going to say that it's about 38 grams per 100 milliliters of water. There's the solubility of sodium chloride. Potassium nitrate at 10 degrees Celsius is the second question. Potassium nitrate's graph, KNO3, is labeled up here, so it's this graph that drops dramatically. It changes solubility quite a bit with temperature. And at 10 degrees Celsius, that's this temperature on the x-axis, 10 degrees, we go up to that curve, which would be right about there. And now on the y-axis, we can see we're between 20 and 25 grams per 100 mils. And I think it's slightly closer to 20. So right in the middle of 20 and 25 would be 22.5. So if it's slightly closer to 20, I'm going to say 22 grams per 100 milliliters. Now usually on a test I would give you leeway of plus or minus 1 in terms of reading the graph, so you don't have to have this exact same result. If you said 23 or even 21, you would get full marks for that on a test. Sodium nitrate at 35 degrees Celsius. Sodium nitrate is this salt here. Na is sodium and NO3 nitrate. And the temperature again was 35 degrees Celsius. So on the x-axis, 35 degrees is here. And if we go straight up to the graph where sodium nitrate is, we reach this point here. And now over to the y-axis, we can see we're between 95 and 100. And so we are slightly closer to 100, so probably about 98 grams per 100 milliliters. One more, potassium chloride in ice water. There's two types of situations on this question sheet where the temperature is not mentioned explicitly. Here's one of them. Ice water means 0 degrees Celsius. Okay, water's freezing melting point is 0 degrees Celsius. So if you've got a beaker full of ice and water, the temperature for that will be very close to 0 degrees Celsius. The other one is over here in part F, boiling water, it says, and we know that water's boiling point is 100 degrees Celsius. at atmospheric pressure, so that's a standard pressure rather, so that would be 100 degrees whenever you see the phrase boiling water. So let's do potassium chloride at 0 degrees Celsius. Potassium chloride is KCl, and 0 degrees Celsius is way down here at ice bath, ice temperature. So we drop. I'm going to say it's over here, right on the y-axis, between 25 and 30, slightly closer to 30, I think. So I guess 28 grams per 100 milliliters of water. So those are a few of the questions, just reading the solubility chart. The rest of the questions on the sheet require that you do that same thing as the first part of solving each problem. So number 2 says, what volume of water do we need to dissolve 35.5 grams of potassium chloride at 50 degrees Celsius? So since we're talking about potassium chloride at 50 degrees Celsius, the first thing I'm going to do in my answer is state the solubility. So at 50 degrees Celsius, the solubility of KCl, potassium chloride, is, and now KCl is here, 50 degrees Celsius, so we go up to the KCl curve. There we are. It's between 40 and 45, and it's slightly closer to 45, so probably about 43 grams per 100 milliliters. And again, if you were plus or minus 1 there, you would get full marks for that. Now, the question's asking what volume of water do we need to dissolve 35.5 grams of KCl at 50 degrees? Well, from the solubility, we can see if you wanted to dissolve 43 grams, you'd need 100 mils of water. That's what that solubility means. Since we're only trying to dissolve 35.5 grams, we expect to need less than 100 mils of water. But do you notice that this solubility, 43 grams per 100 mils, actually reads like a unit multiplier. 43 grams of KCl can dissolve in 100 mils of water. So it acts as a unit multiplier. So what I'm going to do is take the 35.5 grams that we were given in the question, 35.5 grams of KCl, and I'm going to use a unit multiplier, and you have to set up your answers like this with this level of detail. So units are shown, formulas are included, the statement of the solubility, and now I'm using a unit multiplier. Your answer has to be done in this format. So I'm going to get rid of the grams of KCl, and I'm going to convert that to milliliters of water, which is what the question is asking. What volume of water? How many milliliters of water? This unit multiplier is my solubility. So there were 43 grams of KCl for every 100 milliliters of water. And now I'm going to grab a calculator and simply fit 35.5 multiplied by 100, the number on top of the multiplier, and divide by 43, the number on the bottom of the multiplier, and I get this answer, which is in a fraction form. There's the answer in decimal form. So now, how many significant digits should I keep in that answer? How should I round it off? Well, the solubility here said 43 grams, so only 2 sig figs there, and there were 3 sig figs in my original mass, so I'm going to keep just 2 significant figures in the answer. So 82.558 will become 83 milliliters of water. Now, if you kept 1 extra digit, 82.6, that would be fine. You're allowed plus or minus 1 sig fig on most questions. So now 83 mils of water is my answer, but I want to see a little statement with that. So let's just add a little statement that makes sense. This many mils of water are needed to dissolve. Over here we began with 35.5 grams of KCl, and our temperature was at 50 degrees Celsius. So there's a complete answer. On a test, this might be worth 2 points. You'd have half a point for telling me your solubility like that. You'd have half a point for setting up your unit multiplier with the units shown like that. You'd be given half a point for the answer with the correct number of significant digits and a label like that. And then you'd be given another half point for a statement that makes sense, that describes your answer. So there's a complete 2-point question. Question number 3, let's go a little faster. What volume of water do we need to dissolve 75 grams of potassium nitrate at 30 degrees? Pause the video and see if you can set it up, because it's very similar to the one we just did. So I'll say at 30 degrees Celsius, the solubility of, now potassium nitrate is KNO3, is, and now I'll go to my graph, KNO3 is this curve here that drops dramatically. So at 30 degrees Celsius, yep, here we are, 30 degrees, that curve is right here, and so it's just slightly less than 45. Maybe it is 45 actually. Yeah, so I'm going to say slightly less. I'll say 44 grams per 100 mils of water. Now again, if you said 45, that would be fine. Our final answers will be different, but that's fine. So now that comes my unit multiplier. The question said I've got 75 grams of potassium nitrate, and again, the solubility was 44 grams in 100 mils. 75 grams is going to need more than 100 mils, right? It's going to need almost twice as much. So let's set up our unit multiplier. We'll get rid of the grams of potassium nitrate, and we'll ask how many milliliters of water are needed to dissolve that. The solubility says 44 grams of potassium nitrate for every 100 milliliters of water. Grabbing your calculator now. So 75 times 100 and divide by 44. And again, the solubility here limits our significant digits to 2. 44 has 2 digits. So 170.45 will become, I'll switch it to scientific notation to get 2 digits, 1.7 times 10 to the 2 milliliters of water. Now if you said 170, that would be fine. Now a little statement, this many mils of water are required to dissolve the potassium nitrate at 30 degrees Celsius. Your statements don't have to be identical every time. Try to mix them up a little bit just so that you're not memorizing and regurgitating the same thing in every problem. Okay, the idea of that statement is to make you stop and think, what exactly did that answer represent? And that, of course, comes from the original question. I'll skip to question number 4, and I'll go down to number 5, a slightly the reverse type of problem. What mass of sodium hydrogen carbonate, so this time we're looking for mass, not volume, can dissolve in 350 ml of water at 80 degrees Celsius? So sodium hydrogen carbonate is our salt, so I'll say at 80 degrees Celsius, the solubility of sodium hydrogen carbonate, that formula is on my solubility graph. Here it is, NaHCO3, and we're at 80 degrees Celsius. So the solubility there is pretty much almost exactly 20. I'm going to just look a little closer, maybe slightly less than 20. I'll take 19 or 20. I'm going to say just 20 for the simplicity's sake, is 20 grams per 100 milliliters. And I'll remember that that's got 2 significant digits in it. Now, this time we were told the amount of water we have, so I'll start with that, 350.0 mils of water. And using the solubility as a unit multiplier, we'll get rid of the volume of water this time, and we'll find how many grams of sodium hydrogen carbonate can dissolve in that. Now, some mental math, if 20 grams can dissolve in 100 mils, then 40 grams would dissolve in 200 mils, 60 grams would dissolve in 300 mils, 80 grams in 400 mils, so in 350 we're expecting between 70 and 80, between 60 and 80 is going to end up being 70 is our answer. So just some mental math, I can see that. However, I want you to set up your answer like that with the unit multiplier. So 20 grams in 100 mils. Not every question is easy to do in your head like that. So 350 times 20 divided by 100, and surprise, surprise, the answer is 70 grams of sodium bicarbonate can dissolve in 350 milliliters, that's what we began our answer with, and that's what the question told us, of water at 80 degrees Celsius. Another way to have said that is that if we had 350 mils of water at 80 degrees Celsius, we would need 70 grams of this sodium hydrogen carbonate to create a saturated solution. That's how much would be able to dissolve in the water. So that's how much we need to make a saturated solution with 350 mils of water. Question number 6. Actually, why don't we skip that and go to number 7. What mass of potassium nitrate can dissolve in 15 liters of boiling water? So there's a couple things here that make it slightly tricky. Liters instead of milliliters, and boiling water. It didn't tell us the temperature. But we remember that boiling water means 100 degrees Celsius, so at 100 degrees Celsius, the solubility of potassium nitrate, KNO3, is, and grab our graph, KNO3 is here. 100 degrees Celsius is the highest temperature on the graph. So if we go up, all the way up to KNO3 at 100 degrees Celsius and then go straight over here, I think it's slightly higher than 245. I'll take 245, but I think it's probably 246. So 246 grams per 100 milliliters of water. And that's the highest solubility on that chart. Now, we have 15.0 liters of water. That's a lot of water. So we're going to be able to dissolve a lot of this salt. So if we take 15.0 liters, and because we weren't given milliliters, we're going to start with a unit multiplier just to convert the liters to milliliters. Now that I've got milliliters, we can do exactly what we did above, get rid of the milliliters of water and switch to grams of potassium nitrate. So there's my unit multiplier set up. There's 1,000 milliliters in 1 liter, just like there's 1,000 years in a millennium. Milli means 1,000. Mil means 1,000. So the solubility here, grams in volume of water, 246 grams of potassium nitrate for every 100 milliliters of water. Now grabbing our calculator, we have 15.0 or 15 on the calculator times 1,000 to convert to milliliters times 246 and divide by 100, and I get 36,900 grams of potassium nitrate. Now if I switch that to having only 3 significant digits, there were 3 digits in the volume and 3 digits in the solubility, so we'll switch it to scientific notation, I guess. 3.69 times 10 to the 4 grams of potassium nitrate can dissolve in 15 liters water at 100 degrees Celsius. Now if you wanted to tack on one more multiplier and convert that grams, because the answer is so big, to kilograms, that would be perfectly acceptable. then your answer would have been 36.9 kilograms. 36.9 kilograms. Now notice something here. If somebody had said 245 as their answer for solubility instead of 246, how would that have affected the result? Because there's going to be such a large volume, 15 liters, you're going to see a large difference in your answer. So if we take 15 liters again times 1,000, and this time multiply by 245 instead of 246, so a very small difference in the solubility, look at our answer. Instead of 36,900, we get 36,750. So there's a difference of 150 grams there. And you might think, well, my answer is significantly different. If you did this on a test and said the answer is now 3.68 times 10 to the 4, you're going to get full marks for that, right? So small differences in solubility can make large differences in the final result when you're dealing with large volumes of solvent or large masses of solute. So there's an introduction to using unit multipliers and reading the solubility chart to solve solubility problems in our solubility unit. The questions are going to get a lot harder as we go. They're significantly more difficult. These are the easiest level of problems, so be sure you're able to handle these comfortably before you move on to the more difficult questions.